Alright, this is the video for the Unit 3 practice exam. Question 1, this is from section 4.1, exponential functions. This one specifically is graphing. So you'll recall when this was presented, basically broke it down into 3 steps. First, find the horizontal asymptote. Normally it's right here on the x-axis, unless there's some transformation to the function, which there is here. There's a -1, so that moves the horizontal asymptote down 1 unit. It does say give an equation of the horizontal asymptote right there, and that equation this time would be y equals -1. The second step was to find the y-intercept. The way that you find the y-intercept, if you remember, is letting x equal 0. So 3 to the 0 minus 1 equals 1 minus 1, which is 0. So the y-intercept is 0. So I'm going to keep track of the points here. We have the y-intercept when x was 0, y was equal to 0. And then it says plot several other points. Remember what we talked about during this lesson was you need to have the y-intercept and then 2 more points. So I'm going to let x equal 1. 3 to the first power minus 1 equals 2. Okay. Now we'll do if x equals 2. 3 squared is 9, 9 minus 1 is 8, so 2 comma 8. There's 1 comma 2, and then 2 comma 8. Okay, then ask for the domain and range. Domain for any exponential graph is -infinity to infinity. The range is not including -1 to infinity. Alright, question 2 is from section 4.3, graphing logarithmic functions. So I also broke this down into 3 steps. Step 1 was to find the vertical asymptote. Usually that's right here on the y-axis, unless there's been a transformation that moves the graph left or right. And there has been. This transformation here moves the graph 2 units to the right. So the vertical asymptote is at x equals 2. Now, next step is to find the x-intercept. You find the x-intercept by letting y equal 0. So in that case, you solve an equation. Instead of f of x equals 0 equals log base 3 of x minus 2 plus 1. Now solve for x. So subtract 1 on both sides. Then use a base of 3. 3 to the negative first power is 1/3. And then add 2 to both sides. So 2 1/3, or 2.3. So the x-intercept would be right there. And we need a couple more points. I'm going to let, let's see, we need to plug in values for x such that when you subtract 2 from it, you get multiples or a power of 3. So if I plug in 5, for example, right here, 5 minus 2, that's going to be 3. Log base 3 of 3 is equal to 1, and then 1 plus 1 is equal to 2. So 5 comma 2 know that 5 comma 2 is on the graph. And Even though you typically plug in values for x, you can also plug in values for y. Since the range is going to be all real numbers, there aren't any restrictions on the range. So I'm going to go ahead and see what happens when y equals 1. So if I plug in a 1 for y, and subtract 1, use a base 3 on both sides. 3 to the 0 power is 1. 1 equals x minus 2. Add 2 to both sides. So then x equals 3. When y equals 1, x is equal to 3. So 3 comma 1 is on the graph. Domain is not including 2 to infinity. And the range is all real numbers. Okay. Question 3. Simplify each expression. So this particular problem is from 4.4. The other two are from 4.3. The trick to this one is to combine. So if we're using the product property, since there's an addition sign between the two, we multiply what's inside. 25 times 2 is 50. Now if we continue to condense, now that there's a minus sign, we use the quotient rule. Quotient rule says you divide what's inside. Log, and remember, if it's log, common log of the base, remember it's base 10. Log base 10 of 10 is equal to 1. Now on 4.3, the key here is we do have a log base 7, and then there's a base 7 here, but they don't cancel each other yet. We've got to do something with this negative 2. Negative 2 coefficient, remember at one point was an exponent, so I'm going to go ahead and rewrite that negative 2 as an exponent. Now the base 7 cancels log base 7, and we have 3 to the negative 2, which is 1/9. Okay, the trick on part C is to remember that roots, square roots, cube roots, any type of root, they don't mix well with logarithms. So go ahead and change that to 8 to the 1/2. And then we got to try to match bases here. Base 2 and an 8. 8 is a power of 2. So instead of 8 to the 1/2, I'm going to write that as 2 cubed to the 1/2. And then when you have a power raised to a power here, you multiply. So 3 times 1/2 is 3/2. Now the log base 2 cancels with the base of 2. And we're left with 3/2. Okay. This is from section 4.4, expanding logarithms. This is going to be an application of the product property and then the power properties. It's x to the third multiplied by y to the fifth. So this is going to be log base b of x cubed plus log base b of y to the fifth. Now we use the power property to bring those exponents down in front as coefficients. So log base b of x plus 5 log base b of y. For part B, we've got a quotient right there, so we've got to use the quotient rule. Log base b of x minus log base b of y times z. Now we have a product here that we need to expand using the product rule. So this is going to expand into logarithm log base b of y plus log base b of z. But you've got to really listen because this is a very, very common mistake. This minus sign here, Here it is. You're subtracting this entire logarithm. So you also need to subtract this entire expression. The common mistake I see students make is just putting a minus sign there and writing it like this. The problem is, if you write it this way, you're only subtracting that first logarithm. You're not subtracting this entire expansion. So in order to subtract that entire expansion, this has to be in a parenthesis. That way you're subtracting this logarithm and you're subtracting this logarithm, and you have to subtract both because you're subtracting them both here. So just make sure that you make that very clear. Okay, question 5. This is from 4.5 and a little bit from 4.2 when we learned about continuously compounding interest, but more from 4.5, solving exponential equations. The key phrase here is compounds continuously. This should be an indication to you that we're using this formula. And then it says, what interest rate do you need? So we're solving for the rate, which is a variable in the exponent. So in order to solve for a variable exponent, you're going to have to use logarithms. So we want our money to double. If we started with 10,000, then the future amount A would be double that, 20,000. And that equals E, and we don't know the rate, so we leave that as a variable. But we want it to double in 30 years. Okay, now we solve for R here by using the same techniques we learned in section 4.5 to solve an exponential equation. We isolate the exponential term. This is the exponential term right here. We need to isolate that by dividing by 10,000. So that's 2. Now we use a logarithm to cancel the base here. We're going to use natural log. So log 2, natural log of 2 rather, equals R times 30. Now we solve for the variable by, in this case, dividing. So the rate is the natural log of 2 divided by 30. And then calculator, natural log of 2 divided by 30 is 0.023 or 2.3%. Okay, question 6. These are also all from 4.5, solving exponential equations using the same 3 steps. Isolate the exponential term. This is the exponential term here, so we're going to add 3. Now use a logarithm to cancel the base, so log base 2. So log base 2 of 27 equals 3x minus 1. Now we've got to add 1. And remember, you can't add 1 to that 27. It's just got to be log base 2 of 27 plus 1. And then we divide by 3, divide the whole thing by 3. So the exact form of this solution is log base 2 of 27 plus 1 divided by 3. This is the exact form. The approximate solution, again, going to the calculator. Actually, let me go back here. Remember, calculator doesn't do log base 2, so you're going to have to use change of base formula. So log 27 divided by log 2, then plus 1, then divide that all by 3. That's how you would have to type that in on a calculator. So log 27 divided by log 2, then plus 1, then divide by 3, 1.92. Okay, part B, this is the exponential term here, e to the 0.1x. So I've got to get rid of this 9. Then divide by -2. Now use natural log to cancel the base e. So 0.1x equals natural log 4, divide by 0.1. So the exact form is x equals natural log 4 divided by 0.1. The approximate form, the natural log of 4 divided by 0.1, which is 13.86. Okay, I threw on part C here. This is an advanced problem. It's counting as extra credit. There will be one like this on the exam as well that'll just count as extra credit. You can try it if you want. So we're going to use logarithms, but we don't have the same base. So this is a little bit more advanced here. We're going to do. So the key here is to choose one of the bases that you want to cancel, either a base 3 or a base 5. Doesn't really matter which one. I'm going to choose to cancel a base 3. So I'm going to use a log base 3 on both sides. So the log base 3 cancels that base 3 on the left, leaving x plus 2. The log base 3 does not cancel the base 5 there, but if you remember from section 5.4, one thing a logarithm can do using the power property is the exponent can drop down in front of that logarithm. So you can write this as x multiplied by log base 3 of 5. Now we're going to rearrange this equation to get all the terms that have an x variable on the same side. So I'm going to, this whole term right here, I'm going to move it, this whole term, I'm going to move it to the left side by subtracting, and then that plus 2, I'm going to move that to the right side by subtracting. So what it'll look like is x minus x log base 3 of 5 equals -2. And then looking at this side of the equation, both of those terms have an x that I'm going to factor out, leaving 1 minus log base 3 of 5 equals -2. And then to get x by itself, we can divide by this term here. So x equals -2 divided by 1 minus log base 3 of 5. That would be the exact answer. And then plugging this into your calculator, we need to know what the log base 3 of 5 is. So that's a change of base. So we need log of 5 divided by log 3. So that's 1.46. So then -2 divided by 1 minus that answer. It's about 4.3. Okay, question 7. Solving logarithmic equations. This is also from section 4.5. The first step was to isolate the logarithmic term. So that log base 3 is already isolated. There's nothing in front of it as a coefficient. There's nothing add or subtracting to it that we need to move over. So use just a base 3 on both sides to cancel the logarithm. 3 to the 4th power is 81. And then solve for x. Now, with part B, we have multiple logarithms on the same side of the equation. We talked about this, that you have to isolate the logarithm, and sometimes that involves condensing multiple logarithms into a single logarithm. So we need to isolate this logarithm into one single logarithm using the product property because they're adding right there. Product property means that the expressions inside the logarithm are going to multiply. Now that we have one single logarithm that equals one single logarithm, that's considered isolated, so we can use a base to cancel the logarithm. We're going to use base 10 on both sides. Base 10 cancels the common log. So now we have x minus 3 times x plus 2 equals 4x. Now we solve the equation for x. No longer need to use logarithms or exponentials. This is going to turn out to be most likely a quadratic equation. So if we distribute here, we're going to get x squared minus x minus 6 equals 4x. Subtract the 4x, we can get one side equal to 0, and we get x squared minus 5x minus 6 equals 0. And then factoring this would be x minus 6 and x plus 1 equals 0. So then right now we have two possible solutions of x equals 6 and x equals -1. You need to remember we did talk about in class, it's not so much important if these numbers themselves are negative, but when you plug something into a logarithm, it can't remain negative. So we need to check these. 6 minus 3 is 3, so it's fine there. 6 plus 2 is 8, so it's good there. 6 times 4 is 24, so they're all positive with 6, so 6 is fine. -1 minus 3 is -4. You can't take the log of -4. So x equals -1 is what's called an extraneous solution. It doesn't work. So the only solution that works there is x equals 6. Okay, question 8 from section 4.6, applications of exponential functions. We have exponential growth situation, and it gives us a specific doubling time every 40 minutes. If you remember from the discussion in section 4.6, when we're given a specific doubling time, then the amount at any time t is equal to the starting amount times 2 to the t over x, where x is that doubling time. In this case, it's 40 minutes. So we could say the amount at any time t is equal to the starting amount, 3,000, times 2 to the t over 40. So this is the function that models the amount of the bacteria at any time t. So this answers the first part, find a function. But then it says use that model to find the number of bacteria after 10 hours. And this is where students run into trouble. This is a measurement of time, but the problem is it doesn't match with the unit of measure, because our doubling time is in terms of minutes, and this is in terms of hours. We can't mix units of measure, so we need to turn 10 hours into minutes. So 10 hours times 60 minutes would be 600 minutes. So now the amount after 600 minutes is equal to 3,000 times 2 to the 600 over 40. And this is now calculator. 600 divided by 40, 15, so 2 raised to the 15, and then multiply that by 3,000. 98,304,000. Okay, question 9, this is from section 4.7, applications of logarithmic functions. It's talking about rainwater, the hydrogen ion concentration is 10 to the negative 5.6. So there's our H plus value. Use the model, calculate its pH. So pH so the exponent here can move down in front of the logarithm, and then the log base 10 would cancel the base 10, and we have a negative times a negative, so this just equals 5.6 on the pH scale, so it is slightly acidic. Remember, 7 is neutral, anything less than 7 is acidic. So relatively easy question there. Okay, question 10. This is from 4.6, an application of exponential functions. Nice thing about this problem is the function's given to us already. We don't have to build a function or a model, just have to use the model. How long will it take for the population to reach 5,000? How long will it take is a question of time. So they're asking us to solve for t, and they're giving us a population of 5,000. That value goes here for the number. So 5,000 equals, that looks like 10,000. 1. So we're essentially just solving an exponential equation now at this point. So I would want to cancel the fraction by multiplying both sides by the denominator. It's going to cancel it there. So I've got 1 plus 19e times 5,000 equals 10,000. I'm going to divide by the 5,000. So now I've got 1 plus 19e to negative 1.56t equals 2. I'm going to subtract 1. So if you remember the steps now to solving an exponential equation, we need to isolate the exponential term, which is there. Isolating that means subtracting 1, then dividing by 19. So first I'm going to subtract 1. Now I've got 19e, negative 1.56t equals 1. Divide by 19. So e, negative 1.56t is equal to 1/19. Now cancel the base using natural log. And then divide by negative 1.56. So t is equal to natural log of 1/19 divided by negative 1.56. So on the calculator, natural log of 1/19 divided by negative 1.56 is 1.89.